Good day, everyone. Today, our topic is all about properties of sigma notation. So, in our previous meeting, we already discussed the introduction of the sigma notation, wherein we are able to discuss there on how to expand a given sigma notation. And if we are given with an expanded form, we discussed there on how to rewrite it compactly in sigma notation. So now, the very first sigma notation or sigma notation property or property of the sigma notation that we're gonna be discussing is if we have summation of I where I ranges from 1 until n. As we observe is if we expand this 1, this can be written as when I is equal to 1, when I is equal to 2, plus when I is equal to 3 until when I is equal to n. As we observe, this series is just an arithmetic series wherein your common difference is just 1. And as we remember, in the arithmetic series, the formula is just S sub n is equal to n times your first term plus your second term all over 2. So here, the last term that we have is n. It's n. The first term is 1. And the end is still n. So it will be n times the first term is 1, the last term is n, all over 2. Or it can be written as n times n plus 1 over 2. Therefore, if we are given with summation of I, where I ranges from 1 to n, it can perform easily by just using this formula. How come that this formula is useful? Okay, say for example, you are asked to find what is summation of I, where I ranges from 1 to 5. In this case, it's just easy because you just change I from 1 until 5. So you will have 1 plus 2 plus 3 plus 4 plus 5. It's very easy to solve. Actually, this is just 5, 10, 15. The answer is 15. But the problem is, what if you are asked what is summation of I, where I ranges from 1 until 59? Or for example, let's have here 100. So it's hard now because though it's manageable, but it will take you time to simplify it. So if you're gonna be using the expanded form, so for example, you will be using that one. Still, we will use the expanded form being discussed in the previous video. As you observe, when I is 1, you have 1. When I is 2, 3, and so on until 100. Then you will be adding all of those, and it will take you enough time, a long time, a long period of time in simplifying it. But if you will be using this formula, you will just have summation of I, where I ranges from 1 until n. And your n here is 100. As stated in the formula, you just have to follow this one. You just have to know what is your n. Your n here is 100. So it is just 100 all over 100 plus 1 over 2, right? So after that, this is just 50. This is just 101. So you have 50 times 101. So you have 50 times 100. So you will have there 500. Then 50 times 1, 50 times 1. So you have 5. So you have there a 505. Okay. So it's easy if you will be using this one compared than this. So that's the used why that's one of the practical application why we are discussing this sigma notation. It can make our life, our computation more easy. Okay, let's remember that formula. Then we'll now proceed to the next one, the this one. The next is the summation of f of I of c summation of c times f of I, where I ranges from m to n, is equal to c summation of f of I, where I ranges from m until n. Or in this c is any real number. This c here. So as you observe, if you have something like this, you can set aside the c beside your summation. You can set aside the constant. How come that it is possible? So we will be showing here why. So let us start from the left side. We will be proving it. We start from the left side and we will derive the right side. So if you have c, no, not c, but summation, start from the left side. Summation of c f of I, where I ranges from m until n. If we will be expanding the left side, it can be written as first when I is equal to m, the very first term. So c times f of m plus next when I is equal to m plus 1. So c times f of m plus 1. Next is when I is equal to f is equal to m plus 2. So it will be c times f of m plus 2. And so on until the last term, which is when I is equal to the last term n. So c times f of n. As you observe, in each term, c is common. So in that case, you can set aside the c. So it can be written as c times the quantity of f of m plus f of m plus 1. You just factor it out. And so on until you will reach the f of n. Then inside can be written in can be written compactly into a sigma notation. It can be written as c summation of f of I, where I ranges from m until n. That's why it is true. So we are then proving it so we can use it in our computations later. Let's proceed to the next slide. The next property that we will be discussing is the summation. As we observe here, we have summation of f of I of two functions, f of I plus g of I, where I ranges from m until n. So the first is we will be starting from the left side, summation of f of I plus g of I, where I ranges from m until n. First, when I is equal to m, so you will have f of m plus g of m. That is the very first term. That is when I is equal to m. Plus, next is when I is equal to m plus 1. So you will now have f of m plus 1 plus g of m plus 1. And so on until you will reach the last term, which is when I is equal to n. So you will have f of n plus g of n. And then you can easily remove the parentheses. In a way, the operations here are just addition. So you remove all of the parentheses and you can regroup them. We will combine all f function f. So you can write it as f of m plus 1, and so on until the last one, which is the f of n. Something like we just get the first term in each group. Plus, we will get the last term, the second term in each group, the g of I. G of m plus g of m plus 1, and so on until you will have the g of n. So, as you can see, this one can be written compactly into sigma notation. It can be written as summation of f of I, where I ranges from m until n. And also this that can be written as summation of j of I, where I ranges from m until n. That's why it is true. So we can use that in our computation later. So we already discussed 3 properties. We will have more. Let us have this one. This summation can be used if the function here is a constant function, something like f of x is equal to 5. This is a constant function. So what you're gonna be doing is you just have to multiply the constant by this term. How? You just have to get your n, substitute it here, you get your m, and you write it here. Example, I'll give you an example. Example, summation of 3, where I ranges from 2 to 6. So commonly, this can be used if your I is not starting from 1. Say for example, you started from 2. You just have to use this one. So what you will do is you need to know first what is your n. In this case, your n is 6, your m is 2, and your c is 3. So you just have to follow the formula. First, your c, which is the 3. So you have 3. Your n is 6. So you have 6. Your m is 2 plus 1. It's always plus 1 here. The variable that will be changing here are c, n, and m. The one is always fixed. You have now 3. It's 4 plus 1, it's 5. So you have 13. Okay, it's easy. And the next one is the summation of the constant, but it started with when m is equal to 1. Actually, it's if we're gonna be proving it, it's just easy also because you just have to if you will expand the summation of c, where I ranges from 1 until n, the very first term is the constant c. The second term is also c, and so on until the last term when I equal to n is also c, because it's the constant. And if you're gonna be counting how many c's are there are n numbers of c. So if you can, as we all know, multiplication is just a series of addition. So it can be written into multiplication. It can be written as n times c. Therefore, if you're gonna be applying it into example, we have an example here, summation of 13, where I ranges from 1 to 10. So if we started from 1, you just simply multiply the n and the c, the constant here, and the upper bound. So you just have to multiply 13 times 10, or simply 130. Just simple as that. It's very easy. Okay, so we already discussed 5 properties. Let's continue to the next part. Okay, the telescoping sum. We will be giving example for telescoping sum the next video, but we will just have to prove it first here. Okay, the telescoping sum states that if you have summation of f of I plus 1 minus f of I, where I ranges from m to n, this complicated sigma notation can be easily written into a simple function or simple form of f of I plus 1 minus f of m. You just have to get your n, replace it here, and your m, replace it here, then evaluate that with the function being defined here and with the function being defined there. Just simple as that. But let us prove first why it is possible. But before we will prove it, let me share to you that this telescoping sum is very important because it may solve a lot of problems. Aside from solving a lot of difficult problems, it will also be the key in deriving some properties in sigma notations. Example, it can derive the formula for summation of I squared, where I ranges from 1 to n. It can also derive the formula for summation of I cube, where I ranges from 1 till n. It can also derive the formula for summation of I to the fourth power, where I ranges from 1 until n, and so on. So without the telescoping sum, we will not be able to get the formulas of this one. And as we will observe, we cannot solve problems in sigma notation involving quadratic without this. We cannot solve problems involving cubic functions without this, and so on. So it's very important to have the telescoping sum because it will derive all of this. Okay, let's prove first how we get the telescoping sum. So maybe we will have uh okay, the telescoping sum. So here, as we can see, we will start from the left side, then going to the right side. So maybe we should stop sharing. We will have some whiteboard to use because we need enough space in doing it. Okay, start here. So let's start. Let's write first the telescoping sum. Telescoping sum states that summation of f of n plus f of I plus 1 minus f of I ranges from m until n is just equal to f of n plus 1 minus f of m. Okay, so the next thing that we're gonna be doing is the proving of it. So the proof, so first is we start from the left side, the summation of f of I plus 1, I plus 1 minus I f of I, where I ranges from m until n. So the first term here is when I is equal to m. It can be written as f of m plus 1 minus, no, yes, it's when I is equal to m. So it will be, you just replace all i's by m minus f of m. This is when I is equal to m. Next term is when your I is m plus 1. So it will be summation, you just change I by m plus 1. So it will be f of m plus 2. So it will be written as f of m plus 2 minus, when m is equal to m plus 1, so it will be f of m plus 1. The next term is when your I is equal to m plus 2. So you just change this, you will have f of m plus 3, f of m plus 2, and so on until you will reach the last term, which is when I is equal to n. So you have summation of f of n plus 1. You just change I here by n minus f of n. Then we can easily remove the parentheses, and we observe there are terms here that can be simplified. Can you look at here? The first term here, the last term in the second term, in the second group. First group, second group. First term, the last term are the same but in opposite sign. Same as with here, the first and the last. This one, oh wait, it's minus here. It should be minus. Okay. Next is this one and this, and so on. As you observe, the first term, last term, first term, last term, it means this will be canceled out later by the next term. As well as this one and the previous term here. So the only term that will not be canceled out is only this and this, because this one is canceled out in the previous term. So what you will have, what is left is only negative f of m plus f of n plus 1. Or it can be written as we write first the positive f of n plus 1 minus f of m. So the telescoping sum is equal to this. We are done proving it. And that is all for today. Thank you for your time in watching the video, and see you again for the next video. Thank you.